Hi, welcome to the lecture. Um, we're changing topics today. Basically, we've talked enough about UIs and the last project to make some progress on that. I'm going to talk the next 2 days about what's I think is a very important topic, but sort of I'll say it's completely different from what we've been doing recently. So this topic is a problem-solving technique, or called recursion, and it's a style of coding. And so it's basically another way of problem solving. And I think it's an important way to have in your toolkit when you're looking at a problem to think of it in this form. It can lead to insight and sometimes easier solutions. So let's look at an example of this. Early on in the semester, we looked at loops for one form of problem solving. And we had like a search loop and a optimization loop and accumulation loops and things. So it's obviously an important skill to pick up, and important to be able to recognize problems and see how loops apply to this. Um, so can't quite compare with a neighbor here, but let's think about a problem you should already be familiar with. Maybe you haven't done it for an array list, but basically use a loop to add all the numbers up in an array list. And actually take a minute, write it down here for a second, and then think about how you would describe the solution, right? Not in code again, but what are the problem-solving steps that you go through to translate into that loop? All right, so you should actually pause here and like force yourself to do this just for a moment. But we'll continue on. So my guess is that many of you thought about it like start off with some accumulation variable like sum, and then add the first number to sum, and then the second number to sum, third number sum, all the way up to the last number. And when you do that at the end, the sum is the sum of all the numbers, because you've added up all the numbers, and it has the solution, right? And what I want you to realize is that that's sort of a particular way of thinking about the problem, and in some ways that that way of thinking about it is dictated by the computer language. So we have a loop that typically goes over from the beginning to the end, um, and and the way you start to think about recognizing how problems are solved matches that form. Now, another way you could have thought about it would be add up the first through the middle numbers, and then add the middle through the last numbers. And that's still a valid description of solving this problem. It doesn't happen to match that well the structure of a loop, and we in fact don't have really a great way of sort of encoding that solution into the Java language. But it's still a reasonable way of thinking about it. It's actually a way sort of close to binary search, for example, where you split things in half, but in this case it doesn't really apply the same way. So what I want you to be thinking about a little bit is how your own brain has become constrained by learning this language and these forms of this language. And I'd like, it's important to kind of recognize what's sort of a natural thing and what's sort of a constraint imposed by whatever system you're working in. So here's another approach. Add the first number to the sum, and add the first number to the sum of the rest of the numbers, right? So take the first number and add it to the sum of the rest. And in some ways that we can actually capture that way in code. So here we have it's a static method. It's not like really an object-oriented kind of thing. And here we have a list of numbers coming in. I'm using the more general list instead of array list, but it could still be an array list object that's passed to it. And I'm going to return the answer of adding this first number to the sum of the rest. And the sublist forms part of a list starting at index 1 and going to the end, basically. And so this says get the first one and add it to the sum of the rest. So actually we can code that up, I guess. So we already have the top part there, so we're just going to return nums.get the 0 index. And I guess just get a little more space here. sum nums dot sublist, going from index 1 and stopping at the length or size of the list. And that should be nums there. And then we need a semicolon. Okay. So this, in some ways, captures this statement above, add the first number, index 0, to the sum of the rest of the numbers. Here are the rest of the numbers, and we sum them up, right? So down here in main, I have some numbers made into an array list, 2, 4, 6. So using sort of a funny form of initializing it. There's different ways of doing this. So basically make a list out of these and put that list into an array list, and that makes a list, and then I can store it in this numbers, which is really a list reference, but since that's a subclass, we can reference it, you know. And then I pass that into here. All right, so let's run it. And we got an error. And it says index 0 out of bounds. Well, that's weird because there are 3 numbers in the list. Again, it's sort of good to read these error messages kind of carefully. For length 0, well, that's sort of weird. What's going on here? Well, we're shrinking down the list each time, and eventually we get down to an empty list, and we can't. There's no more index 0 there. So you know, we can kind of explore this a little bit by, let's print out the current nums that we're working on. So I'm going to print out calling with, in other words, what's my parameter? Nums. All right, so I'm going to run it again. Still an error, of course, but we start off calling it with 2, 4, 6, which is what we expect from here. And it says pull off the 2 and add it to the sum of the numbers of 4 and 6. And so then all of a sudden we see the calling with 4 and 6. And then what is that sum? Well, it is the pulling the 4 off and add it to the sum of 6. And what's the sum of that? It's pulling the 6 off, and then you get the empty list here. And then we try to pull off the first one of the empty list, and that's an error. All right, so even though this code basically matches this approach here, it's not quite enough to solve this problem, right? And that's because in this statement here, there's sort of an implicit thought, and that is stop when you run out of numbers. So we need to fix the code, and we're going to fix it by stopping when there are no more numbers to get. So if the nums.size is equal to 0, well, what is the sum of an empty array? It is 0. So I can return that directly. In other words, here we have a case that we know about, we know the answer to, and I'm going to encode that. And it's also sort of tells us when to stop. And then I'm going to do the rest of it here. So I'm going to run here, and the sum of 2, 4, 6 is indeed 12, and we see the list of calls here, and it stops at a certain point. Now, this form of problem solving is what we call a recursive solution. In other words, it is a method that calls itself. When I call some nums with some values, inside, as part of the solution, I am calling myself at the same time, right? So it's weird. The definition of the method depends on itself. And in some ways, it seems like, you know, that shouldn't work. But let's see why it does work, right? So first of all, I want to say that I think this is a pretty powerful way of thinking about solving the problem. It's not like, here's a list of numbers, how do you solve it? Well, let's go learn about loops and then learn about indices and learn about this. Instead, we're going to say, the way I solve the problem is to take some small part of it, like the first thing, and then break the problem into some smaller parts so it sort of progresses towards a solution, and make myself recurse on it. And then there's some base case, it's called the base case, that tells you sort of some known stop point, and then the rest of it basically here, right? So typically when you look at a recursive method, you need at least 2 parts, right? There is this base case, It tells you when the recursion stops, in other words, when this calling of itself stops. And then a reduction step. So this is the reduction step here that reduces the size of the problem, and it reduces it towards this base case. In other words, every time we call ourselves, our list gets one smaller, and eventually it's going to hit this, this size 0. Now, one thing that seems a little bit confusing is that there is this parameter nums here, and when we look at it, this parameter nums has 4 different values associated with it. And so how does that work? Well, the thing to remember is that we are passing by value the reference of the objects involved here. And so the nums here really goes on the stack as 4 different spots. Each time we call this thing, a new nums is created, and it references a different sized list here. So it's not like this is the same nums being used over and over again. Every time we call it, we're generating a new local variable, a parameter on the stack, and storing a value in there. All right, so even though the name is the same, they're really different copies of that variable each time that we call it. And so again, don't think that somehow changing nums the 3rd time through the loop, through the recursiveness, is changing the value from some previous time. Those are isolated from each other. These are different values stored on the parameter. Right, so okay, so yeah, base case, reduction step here. And when I have the reduction step, it's really also, it's combining some partial solution with the rest of the solution. I just also like to say that this is going to seem a little bit foreign. It looks a little confusing, and sometimes it actually seems a little bit like magic. But it forcing your brain to think about problems in a certain way, I think, really opens up a lot of opportunities, and we'll see that shortly. We already know how to sum up numbers, so that's not very exciting, but we can do other things with this as well. I'll also point out that, for example, besides the sort of informal learning I'd done on my own about programming, the first formal programming language I learned was Scheme, which is a Lisp variant. And basically everything is defined recursively in there. And we see that a lot in function, this sort of come back in functional languages. This recursive idea shows up a lot. And so again, it's some languages have a sort of a preference for this style, and then you get very good at it. And I think actually it's a good thing to get very good at it. So, and you'll be seeing this more in 2420 for sure. All right, so but you have to remember, if you forget one of these steps, you basically are going to crash your program or go into an infinite loop or something like that. So you have to be careful to make sure to have all the components, the stopping point, the base case, and then the step that actually progresses you towards the base case. All right, so it's also kind of hard to track. I like to track these by hand. How when you call something, like what happens, and normally we would have like sum, and sum equals 2, and then sum equals the old sum plus the new value, and it's equal to 6, and then sum equals 6 plus the new value 6 equals 12, and you can kind of write out on a chart how this all looks, and you have to be kind of a little more careful about how it happens with recursion. So if I call sum nums on a list of 1, 2, 3, this call evaluates to whatever the return value is, right? That's what this expression evaluates to something, and that something is defined by the return in the method. So this call evaluates to the first value, 1, plus the call to a method. Now the method happens to be the same method, but in some ways that's not important to the computer. It's just calling a method. So 1 plus whatever this evaluates to with this data, 2 and 3 inside it. Well, what does this expression evaluate to? It evaluates to whatever is returned from it, which is the first value of this one, 2, plus the sum of the remaining numbers, 3. Well, what does this expression evaluate to? So notice, I haven't figured out what this thing is worth yet, because I'm still figuring out what these evaluate to. So this evaluates to whatever returns out of it, which is 3, the first number, plus the sum of an empty list. This one now, this call of sum nums now triggers the base case because the size is 0. So this call evaluates to 0, which means now we can finally evaluate what this thing is worth, right? This 3 plus some nums. It is equal to 3 plus 0. When I know that, that means that I know what this expression here is worth. This is worth 3. So this whole statement is worth 2 plus 3, which is 5, which means I know I can evaluate what this thing is worth. So this thing is worth 5, and 1 plus 5 is 6, and so this whole call here turns into a 6. But notice it only found out after going all the way down multiple calls to the base case, evaluating it, and then that return value comes back up and builds up the answer as we can evaluate the returns. So there's a lot of deferred stuff going on here. It has to wait till it recurses all the way to the bottom and then propagates those answers back out the returns to get to the final answer. Okay. And again, when you call any method, the parameters and local variables go on the call stack, and the new storage for those, and those new parameters or local variables hold copies of the object references or copies of primitive values. So what are some issues we see with recursion? You forget a base case and you get some sort of infinite loop or crash as you try to evaluate some object that doesn't have data. You run out of stack space. Sometimes you can have a very long recursive sequence and you have to, it just uses a lot of memory basically. And if you're passing a whole bunch of stuff, maybe unnecessarily along with the calls to the recursive method, the copies are made, and that can take up a lot of space. There are ways to convert back and forth between recursive methods and loops. You basically add to a list of values your partial answers and add and remove to the list and sort of make your own stack sort of by hand. Also, if you're naive about it, you can create a lot of excessive and redundant computation. So here's a classic recursive example problem called the Fibonacci sequence. Some of you have run into that in the past. So basically, Fibonacci sequence is a series of numbers, and every new number in the sequence is the sum of the last two. So 0 plus 1 makes us a 1. To get the next number, we're going to add 1 plus 1 to get 2, and then we add 1 plus 2 to get 3, and 2 plus 3 to get 5, 3 plus 5 to get 8, 5 plus 8 to get 13, 8 plus 13 to get 21, right? And these are visualized in different ways. Here we're forming a bunch of squares sort of in a spiral. Actually it spirals this way, and the size of the square is based on this Fibonacci sequence. Now we happen to see Fibonacci numbers in nature a lot. People look at it like this is basically a seashell spiral is based on the same kind of thing. So growth patterns have this. Here are some other patterns of something that matches a Fibonacci sequence, and even like the number of branches on a tree, for example, or something like this. So people are very fascinated by this Fibonacci sequence, and there's a lot of beautiful examples in nature you can find that follow this kind of pattern. So it's one of those interesting mathematical things that looks like sort of a dumb word problem, and all of a sudden it shows up a lot. So it has some deeper meaning, right? So we can express this as some kind of equation where the nth number is the sum of the n minus 1 and n minus 2 in index position, right? N is where it is in the list, and here we can also express it recursively, right? So there's some base case. In other words, at the very end we know the 0 and 1 are important, and then we know how to build up a new number based on the last two. So let's write a Fibonacci. Let's see, recursive implementation. So public static. So we're going to get a number out, the nth number in the sequence. I'm just going to call this Fibonacci or Fib for Fibonacci, and I'm going to pass in n. In other words, give me the 10th number, and the number comes out is the number in the sequence, right? All right, so we know the sort of progressive step, and that is that the nth number is the sum of the n minus 1 number plus the fib of n minus 2. And actually, let me just let's go the other way around, make it go back more and then go forward. All right, so we're saying if I want the fifth number, it is the same as what the, see, the fifth goes to the third number plus the fourth number. Now this would have the same problem as our sum numbers, that there's no stopping it. It would just crash. There's, it would keep going n minus 1, n minus 1, n minus 1 until it ran out of space. So we can say if n is equal to 0, I'm going to do it all in one line, just kind of, I don't know, keep it compact here. If n equals 1, return 1. So there's really two base cases because there's those two starting numbers needed to make this work. And this is really all it is, right? So let's write some code to test this. For int n equals 1, n less than 10, I don't know where that came from, n plus plus, and I'm going to get out an answer and store it. So I'm going to ask for the nth number in the sequence, and let's print out what it looks like. So sys out, and let's kind of make it a little bit nice. Fib of n, so I'm going to make it look like math here, if I can figure it out, is fib n. All right, so I'm saying call this function in a mathematical way with this value like 10 and tell me what fib n is. Hopefully I have enough end quotes and stuff there. All right, so here's a sequence: 1, 1, 2, 3, 5, 8, 13, 21, 34. So that seems pretty good. Now, here's a question. How many times would calling fib4 call the fib function, right? And see, I haven't used my Apple Pencil here in a little while. Let's see if I can remember how to do this. So fib4 is going to call fib2 and fib3, right? To get an answer. So that's going to be a fib2 plus fib3. I don't care what these, what values come out of these. I'm just trying to figure out how many times it's called. So to get fib2, we need to call fib0 and fib1. And those actually turn into values, 0 and 1, so there's no more fib calls at that point. Fib3 calls fib1 and fib2. And then fib2 calls fib0 and fib1. So calling this, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 calls to fib to get the answer for fib4, right? So that should make us a little bit nervous. And in fact, like I said, I sort of ran out of room even trying to sketch that out there. So let's kind of add in, let's add something in to kind of count how many times it's called. So I'm just going to add 1 to some call counter when every time this is called. And I kind of cheated and I made that rather than having to pass it in as a parameter and stuff, I'm just going to have this thing floating around our object, our class. This is a static one, so it's a class variable. that gets called, and we don't have to return it. We don't have to, I'm kind of cheating and misusing the class a little bit here to kind of instrument this method as it runs. So what we need to do now is reset call counter every time through, and then output. The Fibonacci of this is this number, and fib was called call counter times. Right, so I'm going to print out how many times fib was called in recursively while generating this answer. So we can see it grows pretty fast. Fib 4, 9 times, I think is that the answer I got? I don't remember now. But going up one more here, we go up 6 times here. Going up one more here, we go up 10 times here. And all of a sudden we're growing pretty rapidly, right? In fact, let's kind of look at a bigger 40 Fibonacci numbers is not a lot of numbers, right? It's like barely a sequence. If you're like some sort of mathematician looking at sort of patterns in this, you'd be looking at billions of these numbers or something like that. So now to call Fibonacci 39, it's a big number that comes out, right? 63 billion of some kind. But Fibonacci was called 200 million times. So calling something 200 million times to get the 39th number in a sequence, we're going to get into trouble if we try to do anything too big here. We're going to run out of stack space pretty fast. So this is not a particularly good solution. So people like to show Fibonacci as a formulation that's a classic way of, easy to think about recursively in some sense. You just add the last 2 numbers and you sort of compute what they are. And the code in some ways is dangerous because it makes it look really easy, but there's a lot of computation going on underneath. And so this is sort of both a good example and a warning example of being careful about Fibonacci, or this kind of thing where you can get a huge explosion of computation. So there are efficient ways of computing Fibonacci. I mean, after you start building the list, you just take the last 2 numbers and add them to the new list. So doing this in a loop form would actually be very efficient. You're just adding 2 numbers together and adding to the end a new number, and it's like hardly any cost whatsoever. So in some ways, the recursive way of thinking causes trouble here. So let's look at a problem that maybe is, both those problems are problems we could solve pretty easily with loops, and the recursiveness doesn't really provide an advantage, I think. So let's look at a harder problem. I want to draw a tree, okay? And you can sort of imagine like what anyway, how would you do that? Trees are complicated things, right? So in some ways, though, we can kind of recognize, okay, you have a tree trunk, and then it has a branch and a branch. But what does that branch look like? Well, it also has a branch coming off the end of it, and this one has a branch coming off at the end of it. And those branches have like little branches coming off. And so in some ways, like a tree is a trunk, and then 2 smaller trees drawn off to either side. And this is an example what's called a fractal. Fractal is a self-similar shape. In other words, you look at it at different levels of detail, and it looks kind of like the overall thing does as well. So, how to draw this, recursively again, we're going to do something that looks, something, there's a trunk, we go off to the right, and then we come back. And we go off to the left, and then we come back, right? And then actually maybe we want to go back to the beginning again to sort of show where we started. But this thing and this thing, that looks kind of like that whole thing does right there, right? So there's some recursion that goes on here that you say, make me a trunk and then make me a little tree off to the right and make me a little tree off to the left. Now you got to stop at some point, and you basically say, well, when the branches get small enough, just stop. Like if they're as small as you want, or as smaller than a pixel, you can't tell the difference. So stop in that case. And we're going to implement this with a package called Turtle Graphics. A turtle has it was actually built in the 70s at MIT to help teach children about programming. So basically, a robot has a position and an orientation, and you can tell it to go forward a certain amount, rotate a certain amount, and leave a mark behind it with its pen. Okay, so let's make a tree. Whoa, get rid of that. Oops. Okay, so I'm making a window here with a width and height. I'm making a turtle at some starting position and orientation. And I'm not, I can't remember which way 90 degrees is. It's probably straight up. And say it draws on a certain size canvas and some scaling stuff. Now, to draw a tree, we are going to say how long the current branch is. In other words, have we started the main thing, or are we shrinking down for those side branches? And this branch limit is basically when we should stop. So, okay, so since you don't really know the turtle graphics, it's a little hard for you probably to kind of like guess a solution here. But I'm going to say if the branch length is less than the branch limit, in other words, if we have recursed enough that our branches are getting so tiny and they're now smaller than what we think the limit is, we should just stop, right? And the way we stop is we just return and don't do anything. So we're not actually computing something, we're doing something. We're going to draw a tree. So how do I draw a tree? Well, first I make the turtle go forward for the trunk. And it goes forward branch length, distance. Once it goes forward, I want to turn and make that first branch, right? Now the turtle happens to only have a turn left, rotate left command, but I'm going to cheat and make it rotate left by negative branch angle. Branch angle came from the class here, and so it turns 50 degrees. It probably should have been passed along as a parameter. There's no need for it to be part of a class. I think I was just trying to make things be a little more condensed for lecture here. And then at this point, I want to go forward again and do that branch, and then come back. And so I'm going to draw the right branch, but I'm not sure how to do that yet. And then when I've come back, I need to turn from where I am here back to the middle and then back to the other side. So turn left. I already went one amount this way, so I got to go back 2 amounts this way. And I want to draw the left branch. And then I've drawn this tree. I need to get myself back down the trunk, so I kind of go to the beginning again. So I need to turn this way 1 chunk. So I'm going to turn left again, a negative branch angle. And then I'm going to go, I also don't know how to go backwards. I can go forwards, but I'm going to go forwards the negative length. Okay, so we're here. We go forward. We turn right. We draw this branch and then come back to where we were. We go back 2 chunks to turn, draw this branch, come back to where we were. Turn back to the middle, and then go back to the starting point. My hand, this is like my turtle. I don't know exactly why I'm, go back to the starting point. And then I'm done, right? So what should it be here to draw the right branch? Well, I want to draw a tree there, a smaller tree. So what makes it a smaller tree? It is the branch length times the branch scale. And the branch scale is a number that says how much it shrinks. It goes to 60% each time. So this is a percentage kind of thing. I could, instead of doing like -5, where it's also possible to just make it like 5 smaller each time. I'm just making it so it goes down 60% each time. And then I also have to pass in this branch limit. right? Now it's weird that when I say, draw these branches, I'm really saying draw a tree again. So this is the recursive part. This is the base case. The reason it progresses is that the branch length is getting smaller each time because it's scaling down by 60%. And that's all there is to it. All right, so, and goes, now there's one other little thing I want to do and that is, just because of the turtle thing, I want to tell the turtle to show what it has drawn so far. In other words, otherwise the whole tree will just pop into existence and it will be a little more confusing to understand. Okay, so I'm drawing a tree, and in here when I make a tree, I'm just going to call turtle draw tree and give it some initial values. So I'm going to say start off with a branch length of 80 and go until the branches are smaller than 30. Why are you unhappy? Oh, it's not turtle draw tree, it's just draw the tree. Okay. Again, I should probably do this I should probably call it on here like tree draw tree or something like that. Yeah, let's do that. Tree, draw tree, 80 and 30. Okay, so I'm going to run this. Woohoo! I got a tree there. So it quit pretty soon. Let's make the turtle go also sort of in the beginning, in the middle. Turtle go to, so I can make it, I kind of forget how big, 600, so 300 and 100. All right, so go to the middle and then towards the bottom. Turtle go, oh, and its initial orientation, it should have 90. Okay, I guess I should have just constructed it in the correct place. I have an example where I'm making like multiple ones on the same screen, so I had to kind of keep repositioning it. Okay, there's a tree. Now, that is a tree I could have done without recursion, right? So let's try something a little more complicated. Let's go to 200. So the initial branch is 200, and I want to stop when it's smaller, like 15. All right, so hopefully get some more branches going now. Oh, see? So it drew the trunk, it drew a smaller tree off to the right and a smaller tree off to the left, and the smaller tree is also made of a trunk with a smaller tree off to the right and a smaller tree off to the left. And this one is also a trunk with a smaller, or a trunk here and a smaller tree off to the right, smaller tree off to the left, and so on. So it's starting to get some detail in it. And draw a tree. Let's see, what size do I want there? Oh, I want to get bigger here. Let's make the end branches be very tiny. Yeah. Right, let's make it a little bigger. I don't know why I whipped out there. So now we're getting some payoff from the recursion, right? It's actually, it's beautiful. It's fun to watch. But this is a fractal. Every place you look looks like a scaled up or scaled down version of the overall thing. And there are other things we can mess with. So I can change the branch angle. I don't know. What's that? It's gonna do. Spaces out a little bit more. Anyway, there's a lot of things you can do to play with this, right? But notice I get that little short stubby tree, that mid-sized tree, and the big tree all out of this same recursive method that just says make a trunk and make a tree off to the right and a tree off to the left, and then let the rest happen as it will. There's a related piece of code called a snowflake. And a snowflake basically um, has a side that looks like this. But you then replace every straight part with another version of that, and so on. And then you put them together into a full object. And again, that's the kind of thing that, it would kind of drive you batty trying to figure out how to do that like with a loop or something, right? I mean, you'd be like, I'll turn this much, and then what's the angle going to be? And, it gets really, really hard. But the snowflake is really just saying, hey, go forward and draw a little, for this branch, draw a little snowflake that's 1/3 the size, and then turn left and draw a snowflake on this part, and draw a snowflake on this part, and draw a snowflake on this part. And if it's small enough, just draw the raw side itself. But it's just this there's 1, 2, 3, 4 parts. There's 4 recursive calls on this thing, and when you put it all together, you get this is a very famous fractal, right? And it's I think also kind of beautiful and kind of neat to play with. But if I'd gone down, to go down fewer levels, you start to see that again the broader strokes of the pattern, right? And in fact, if I just do the base, so it's each side is go make a little bump and make a side, and then go just rotate it around 3 different sides. But of course, it's the higher ones that are more interesting to look at. I added another layer, so it has to work its way down to the bottom layer before it starts to draw. I thought I'd see something here. I did 5 last time. Maybe that was. Maybe I. Well, I'll leave that up in case something happens for a minute. Okay, so in this class, oh, my face is missing now too. Yeah. In this class, we've learned about arrays and array lists and even hash map, and there's some sort of like natural matchup with loops there, and that's why we talk about loops a lot. And you add in some if statements, and you can kind of do a whole bunch of stuff in there. Now, there are a whole bunch of other data structures in computer science, and for example, trees, which are related to the tree that we drew, heaps and graphs, and in some ways they're a lot more complicated to think about. We have a good mental model of what an array list looks like. It's much harder to understand these ones that are sort of hierarchical and have layers to them. And recursion is a very useful tool for navigating those data structures. And so partly I want you to understand that, hey, there's a lot of CS left, a lot of actually really cool topics to learn about, and this is just a taste of that. But it's going to be important for you at some point to at least be comfortable with that kind of recursion of summing up some numbers and understanding how that works. Well, I don't know why that did not work, but so please look that over, look at the code, and we're going to do some more practical, instead of these sort of fanciful examples, we'll do some more practical examples on the next lecture. Okay, so have a good day, and we'll have a live discussion tomorrow at our normal time, 10:45. Bye.